All right, hello everybody. I'm Ellie. I am the head of R&D at Espresso. And yes, today I'm going to talk about synchronous composability with encrypted and potentially private transactions. So we want synchronous composability across all chains. This is like great interoperability. But can we get it across all L2s, specifically ones that do not, have some sort of encryption or privacy associated with them? Yeah, and so that's what I'm going to try to answer today. All right, so the goal is that you want all L2s to interoperate with each other so that they feel like a unified chain, but you can still have the benefits of many chains, such as horizontally scaling, allowing different VMs, allowing privacy, etc. And I'm just going to really quick go through like what interoperability is today, and to kind of like set the groundwork. And yes, these are the good advantages of having L2s. So the L2s today are very siloed. You can't very easily like send messages between them, and this leads to a lot of fragmentation. Particularly liquidity fragmentation, where each chain has to have its own liquidity. And let's say that I want to do a bridge transaction from rollup B to rollup C. Well, what it would be, an optimistic case of what it would be now is that I have to settle rollup B. That will take, let's say B is a ZK rollup, and let's say it takes about 60 minutes to settle. I think that's what ZK Sync, how often they settle today, is about every 60 minutes. So I have to wait 60 minutes. Then I need to wait for Ethereum finality, which we'll say happened in 13 minutes. And then now I can mint my 100 USDC. And so we're at 73 minutes already, and we still haven't finalized the second side of the transaction. We still have to wait maybe another 60 minutes, and then again for Ethereum finality. So it's really slow, and we don't want this. And if you're an optimistic rollup, it's going to take even longer to do this, 7 days. And so these particularly affect different applications, where you want to say, oh, I want to move my funds over to Polygon so I can participate in Polymarket, but they're actually on another rollup that I have to wait for 2 hours to get my funds, and maybe by that time I've lost my chance to bet on what I want. So here is today all of the different apps that are deployed across many chains. So we have the highest is SushiSwap, and it is deployed across 41 different chains. Now, not all of those are Ethereum L2s, but most of them are. And so, this isn't great. Because it's so difficult to message between chains, these apps have to be deployed on different chains that each have their own liquidity. If you're a small chain, it's very hard to attract liquidity to your chain, and it's not a good experience for users. So what we want to be able to do, briefly, so you do have solvers today that can kind of short circuit this, where they will say, okay, I will front you money on the other chain, and I will take the risk that the money on the first chain will eventually settle. So there's some risk to it. And this provides a very good user experience, but it's not quite what we want. So yes, it has great UX, but it relies on trust. It's not cryptographically enforced, and the liquidity is still fragmented. So going on the second bullet point is that the solver just has to trust that their transaction will eventually settle on the L1, and most of the time it does. But there's nothing that cryptographically enforces that happens. So what we want is composability, where you can just send messages between rollups. You don't have to go through the L1. This is the idea that we want. And so the way I'm going to define composability is very specific, and it is that the state transition function of one rollup uses the result of the state transition function from another rollup. So the key part here is that the state of rollup A depends on the finalized state of rollup B. There's no sort of you're not guaranteeing safety based on economic stake. You're not guaranteeing it based on pre-confirmations. It is literally in the definition of the rollup that it is going to rely on the state of another chain. And this is the strongest kind of composability that you can get. And this is what we want. And then this is an example of how you can expand this, how you may have rollup A may rely on the state of rollup B, and then rollup B may in fact rely on a previous state of A, etc. So in the summary, fragmentation is bad and composability is good. So before we get into the encryption stuff, I'm just going to describe a really basic message passing scheme that we might use to send messages between chains. And the way that this works is that you have an inbox and an outbox on each rollup. They contain messages, and the messages are what's in that yellow box there. It's a payload of arbitrary data plus basically routing information. And the way you enforce that rollup A is consistent with rollup B is that you check if their mailboxes are equal to each other. So you would first check a proof to make sure that the mailboxes have come from a correct execution, and then you would check if they're equal to each other. And that way you can enforce composability at settlement time. So for example, if rollup A minted a token and rollup B did not, their mailboxes would not be consistent and they would not be equivalent, and therefore it would not settle. So yeah, you check the proof, you check the consistency of the mailboxes, and this is all done in a smart contract on the L1. All right, so now we're actually getting into the more interesting part. What about encrypted transactions? And so the message passing design still works, but with some caveats. The message passing design still works. And the key part of why it still works with encrypted transactions, like for example, I'm talking about like a threshold encrypted transactions that get decrypted after they're sequenced. The reason that works is because it's the sequencing that determines the execution. So once you have confirmed and finalized the sequence of transactions, you'll always get a deterministic execution. And you don't have to know the execution of transactions to sequence them. And so, yeah, just quickly the way this would work, you would submit your encrypted transactions to your rollup, and then eventually you would have a threshold committee that would come together and decrypt them. Okay, but let's see how this interacts with this messaging layer. So if you have an encrypted transaction, you don't know what it's going to execute. And the messages in these inbox and outboxes are not known in advance. They're generated from execution. So if your transaction is encrypted, you don't know what's going to be in these mailboxes. So what you can do is that you can sequence the transactions, and then after the transactions have been sequenced, you threshold decrypt them, and then you have what we're going to call a coordinator party. And this party doesn't have any power to sequence transactions. Their job is to just execute both of the rollups and figure out what the inboxes and outboxes are. And with that, this whole consistency check, it still works, and it's quite easy. But you may say, okay, well maybe that's pretty basic. Maybe I want to do something a little bit more. And another thing you could do is you could encrypt the payload inside of these messages. So the metadata is still going to be visible, but the payload can be encrypted, and then it's the job of, say, the smart contract on the other side to decrypt it. And this could be particularly useful maybe, or potentially if you're trying to go, let's say rollup A is just a regular rollup where everything's in plain text, and rollup B is a more private rollup. So you don't actually want to reveal the information that you're sending to B, but you can encrypt it, and then inside the privacy of B, you can decrypt it. So that's another option that you can do. But a caveat to this is that you can't get execution pre-confirmations. So if you have encrypted transactions, you can never get an execution pre-confirmation until they're decrypted because you don't know how to execute them. But the downside of that is that if you're composing with one rollup, like let's say your rollup does not use encrypted transactions, but you're composing with a rollup that does, now you also can't know your state until they decrypt their transactions because your state relies on their state. So that's a trade-off. All right. Now we'll see what about private transactions, and this gets quite a bit more difficult. So a lot of private designs use a UTXO model like Zexi, and this complicates things a little bit, or a lot. So we have our UTXO, transaction tree here. Transaction 1 is, or transaction 2 consumes transaction 1, etc. So if we want to get composability in this same way, where we have these mailboxes and we're checking the consistency between the mailboxes, we need to do a couple of things. One, we need to update the VM logic to allow UTXOs to be consumed in the same block. And some UTXOs models do this already, but not all of them. So if our block is that blue square, we need to allow transaction 2 to consume transaction 1, and then transaction 4 to consume transaction 2, all within the same block. And that's not too difficult of an upgrade, and it's arguably an upgrade that maybe should happen regardless of composability. But I will point out that previously, when we're just talking about regular rollups or even rollups with encrypted transactions, to implement this composability, you didn't need to change your VM at all. You just needed to put a smart contract on the chain, and that works. And the difficult part now is that we kind of now have to require that private rollups change their VM, and this is not ideal. And then number 2 is kind of the bigger ask, and that is you essentially have to allow a UTXO VM to create UTXOs out of thin air, essentially. And the reason is because, let's say I'm doing a mint and a burn. So I burn my transaction on rollup A, and then I send a message to rollup B that says mint. Well, rollup B, is trying to mint something, but it doesn't have any UTXO that's being consumed from. So you have to update the VM to say, hey, if I receive this special message, you can create a UTXO out of thin air. But this is a little bit difficult because it's not quite as generalizable. So in the previous version with just encrypted transactions, you can send whatever data you want. A message between chains doesn't necessarily mean you're bridging or you're minting and burning, it's just whatever data you want. And with the UTXO model, it gets a little bit trickier to do these very general things without having to add a lot of complexity on top for the developer. So in the previous version, all of the developer has to do is call some smart contract that says write transaction to the outbox or read transaction from the inbox, and this one now is a little bit more difficult. And so yeah, here's an example. If transaction 7 basically was the result of some bridge transaction, you would have to be able to insert it essentially with no history. And this is possible, so UTXO models today do allow minting assets, so it's not completely impossible, but you need to make it more general to essentially allow minting any kind of asset or doing any kind of arbitrary logic. And so then to remember, we're creating a global state, but only one that is checked at settlement time. And so the way that this would work in the UTXO model is that you need some coordinator party, like I mentioned earlier, and they basically need to be the one that figures out what transaction 7 is, just like in the other model. But the problem is, is this private? The problem is that this coordinating party can kind of see what you do a little bit. So it's not completely private. Your transaction may still, it may still be confidential and hide the amounts, but you have some party that says, oh, I see that someone is sending from rollup A to rollup B. And it's not ideal, and potentially this party, maybe they could decide to censor you and say, I'm just not going to include your transaction. So this is not ideal. So you can have a UTXO-based private rollup, and you can still get composability, but with some trade-offs. One thing you can do, however, with this coordinator party is that you can run them inside a TEE. And I just want to point out that the TEE is only for a little bit of censorship resistance. It doesn't give you complete censorship resistance, but it basically can enforce that this coordinator runs some algorithm, but that algorithm is not for safety. It's just for like a slightly better user experience to make sure a few more transactions go through. But the key point is that it is not for safety. Whoops. All right, so then the question is, well, can we do even better than this? And I would say that that's an open problem that we're still working on at Espresso. If we have real-time proving, then the problem is really easy. You can just prove you can prove the state of one chain and give it to the state of the other chain. That's really easy. But to do that in a good way that really has low latency, you need very real-time proving, like on the order of 100 milliseconds. Even something on the order of a few seconds would be okay and would offer a decent experience, but it's not quite the same. So yeah, if we get real-time proving, that would fix a lot of stuff, but it's probably not going to happen in the very, very near future. So therefore we have to, so instead of having real-time proving, we have to revert back to the model where you optimistically include your messages that you're sending across chains, and some coordinator does this, and it's only enforced at settlement time. So yeah, I guess that's roughly the end of this, and I guess my question is, if people have ideas about how to maintain privacy better when you're doing a cross-chain transaction in the UTXO model, I would be very interested in hearing about it. This is something that Espresso's only begun to look into over the past few weeks or so. So we haven't completely thought about it, but it's a difficult problem, it would seem, if you want to maintain your privacy. And okay, with that, yeah, thank you.